Okay, so in this final part of the lecture, we will make some considerations about multiple testing, and then we will make a summary. Okay, so let us say that you are screening 1000 compounds versus a control, and for each one of the comparisons you already know how to compute the sample size. The problem, as we saw in the first lecture, is that you will be increasing the probability of getting false positives. So as a family, the false positive uh, rate is much higher than this 5% of just a single test. So on average, let's say that none of these 1000 compounds is useful because you have 5% of false positive rate. On average, you will reject the null hypothesis for 50 of these compounds, even if they are not different from the control. So one possible solution for that is to change the alpha. So you change the alpha this way. So you want the family-wise alpha to be 5%. So the alpha that you use for each one of the individual comparisons is alpha of the family divided by 1000 in this case, because you will do 1000 tests, and this is called the Bonferroni correction. There are other corrections like the Dan-Sidak correction, that is this one, and they're not too different. Bonferroni is sometimes criticized for being very restrictive, so kind of overestimating the family-wise false positive rate. Also, this multiple testing appears when you are, for instance, analyzing ANOVA data. So once you identify that you reject the null hypothesis of the ANOVA, that is, the mean of all groups, at least two of them are different, and you have to find which two are different, and then you would do pairwise comparisons, all versus all. So in that case, K is T over 2, so that is T times T minus 1 divided by 2. This is T groups taken in groups of 2. And so if you compare all the effects versus a control, then you have fewer comparisons, so you have only T minus 1. And then depending on how many treatments you may have a large number of comparisons, and then you have to compensate for those large number of comparisons. There are multiple ways, and here you have the most common ones, that is Taki's honestly significant difference, and if you do all versus all, so all treatments versus all treatments. If you do all versus control, then you use the Dunnett's test. If you do all versus best, you do the Su test. And if you make some unplanned contrasts, then you use the Sheffes test. But these are technically correct ways to address this problem of multiple testing and finding the groups that are different. But the general idea is that the family-wise error, false positive error, is increased, and it is increased by the number of comparisons, and somehow they don't follow the same idea. These tools here, they don't follow the same idea as these ones. They don't use these exact calculations, but they follow the similar concept that you want to reduce the false positive rate of the family. And here is another interesting problem. Let's say that you have T treatments that you will compare to a control group, and then you will do all these comparisons. Doesn't it make sense to put more samples in the control group, because you will use it in many comparisons? So if you make a mistake in the control group, this mistake is carried over to all those comparisons. So you want to be precise in the control group. So the variance of all these contrasts is this one. Now we know how to compute the contrast and the variance of contrast. So that variance is this one. So we may try to minimize that variance of this contrast subject to this constraint. We already know this trick. We use it when we had to compare two groups of different variability. So now the solution of this is that in the control group you should put the number of animals in each one of the groups multiplied by the square root of t, that is the number of treatments. And ni, then the number of elements in each one of the groups, you would use the formulas for the ANOVA contrast, that are these ones, 12 and 13, that we have them here, but with a different normalization. The normalization now is this one, so somehow we have the square root of t there. And you have to remind to use some kind of corrected alpha for accounting for the multiple comparisons, and also the number of degrees of freedom that we have it here. So the number of degrees of freedom here of the residuals, it is this one. It is this one here, in which we account for the fact that we have different number of samples in each one of the groups. Okay, so summary of this part. All the calculations of the sample size when you are comparing means, they all respond to this kind of formula, where you have a term that depends on the confidence level, a term that depends on the statistical power, divided by a normalized effect size. And the simplest normalization is delta divided by sigma, but we have already seen that there are multiple ways to normalize depending on the specific test that you will apply. And we have here set, assuming that the variance is known, but you know that when the variance is unknown, this set is not set, it is t, and then there are known central t involved in the statistical power term, and so things are more complicated, but the concept is this one. And you have to think of whether you have one-sided or two-sided alternatives, and remind always that the one-sided sample sizes are slightly smaller. Whether you have one or two independent samples, and whether you have two samples that can be reduced to one independent sample, so for instance in the paired data or the ANOVA contrast, whether you know or you don't know the variance. Remind that equivalence tests are not the same as significant tests. The equal sign has moved to the alternative, so that now you have two hypothesis tests. And remind that you can increase the sample size if one of the groups is more variable than the other. So, and if you are doing multiple comparisons, remind to decrease the alpha, because otherwise you are increasing the family-wise false positive rate, and increase the control size if you plan to use it in multiple comparisons. And this would be all for the means, and see you in the next lecture.